This conference will now be recorded.
So this is the title of our training, Deep Learning Theory and Practice. This is a quick outline. So each topic here is going to be very deep. Today, it's just the introduction. We'll probably not consume the whole 2.5 hours. So, and then we will see unsupervised learning. Normally, we don't see this in this training, but because we didn't do it last time in the first part, because of that, we are doing it in this part. We are going to have like just 1 or 2 sessions about unsupervised learning. Then we are going to dive in neural networks like MLP, multiple layer perceptrons, gradient descent, backpropagation, dropout, loss functions, and more. Everything that is related to neural networks. Then we will see the models that are used for computer vision. These models are mostly related to CNNs, convolutional neural networks, which is like a subclass of neural networks that is very powerful with images. And after that, we will attack NLP, natural language processing. So this data in computer vision are data that are like 2-dimensional data. It's images. Natural language for processing are monodimensional data. It's like sequential data. So we will have a look at what is bag of words, word embeddings, recurrent neural networks, and this last technology, which is the transformers. So this is in a nutshell what we are going to do. And each part in here is going to be quite deep. So to start by some motivations, like in 2012, like Harvard's Business Review dubbed like data science as the sexiest job of the 21st century. Some works about machine learning, like this is from Andrew Ng. This is one of the famous gurus of machine learning in the world. Just as electricity transformed almost everything 100 years ago, today I actually have a hard time thinking of an industry that I don't think AI will transform in the next several years. Another guy, Mark Cuban, said, artificial intelligence, deep learning, machine learning, whatever you are doing, if you don't understand it, learn it, because otherwise you're going to be a dinosaur within 3 years. Sorry for these words. Also, there are plenty of jobs really available, and there is a very short supply. It's like every company is having a hard time hiring, and relatively it pays well compared to other jobs. By the way, guys, feel free always to stop me. Feel free to ask questions, and like don't hesitate to intervene at some point, even if you don't agree with some point, something I said. Don't hesitate to speak. So, what is deep learning? So it's this class of algorithms that targets some problems that are generally hard to deal with. It's like with traditional algorithms, it's very hard to deal with this class of algorithm, but this class of problems. And deep learning is this algorithm that can solve these problems. For example, this is a biker. Traditional algorithms will struggle a lot to know that this is a biker. It will be very, very hard for them. This kind of problems are tackled with deep learning. Speech recognition. Traditional algorithms also like struggle with speech recognition. There are models that performs well, but deep learning is like a natural fit for it. Text, web search. There are old methods that we are going to analyze and see, but with deep learning, we can do a lot more. The types of results that we can get are at different scales. So it's like this kind of deep problems that are not easily expressed by rules. Rules mean if then else. So, for example, if we wanted to recognize this is grass, it's very easy in the first image. If it is green, then it is grass. It's so simple. We can express it with rules. But if we want to recognize the biker, it's expressing this with rules is almost impossible. And deep learning is one of the strong solutions to deal with this kind of problems. Any questions here, guys? Any question?
No, so far.
Perfect.
What's the difference between deep learning and, let's say, previous algorithm that we use to resolve problems?
Yeah, we are going to see that. Like I said here, previous algorithms try like to solve a problem by transforming it into an if then else rules. If it is green, it is grass. If it has this shape, if it is a square, then this. I'm oversimplifying it, but this is what traditional algorithms try to learn. It's like you have to prepare the features for them. But with deep learning, can you tell me why this guy is a biker? Tell me why this guy, you cannot recognize it, Yunus. This guy is a biker.
Because he's riding a bike, basically.
Yeah, but you could recognize a bike. You could recognize a person.
Yeah.
It's very hard to explain what makes a bike.
Because we based on our knowledge, because we know we compare this image with our database of image, and we find that that's a bike. This is what we do.
Okay, good answer. But I'm going to show you that it is even more complex than that. Let's move on.
I was going to tell is like if we have to recognize, for example, the wheels, it's like the body. I don't know. It's like
exactly, you decompose it. You see the wheels. You see a shape. That it's like you see different parameters, different features that makes a bike.
Okay.
So that's what you do. But with traditional algorithms, it's very hard for them to see these things. You have to handcraft certain things. That this is a wheel. This is etc. But I'm going to show you something like. That is more meaningful. So generally, with traditional algorithms, like in here, but those that we saw in the first part for those who attended it. So we have the more data we add, the more performant the model is. But at some point, the model starts not like to generalizing more, not improving, even if we add more data. So to improve here, after this point, you need better models. You can't rely on these traditional algorithms anymore because you're adding data and still nothing is happening. You are not improving anything. In these cases, when you don't see any improvement, even when you add the data, this means that you can apply deep learning methods. It is not improving. If you use deep learning methods here, it also means that you need a lot of data. And traditional algorithms, as you can see, they do slightly better here than deep learning. They are slightly better when you don't have a lot of data. But at this point, deep learning starts exploding. The difference is huge.
So Reda, does it mean that we use deep learning when we have like massive data?
Yeah, when you have a lot of data and processing power, and you have a lot of processing power. So you can see with traditional methods, when you have just a little bit of data, it's better to use them. They are slightly better than deep learning. But at some point, when you don't see any improvement, it means that now it's time to use deep learning. If you need more improvement, okay? So this is one way of using, or one case when using deep learning. So you need a lot of data, and processing power will be needed a lot, and we are going to see why. So why do we use them? So they are biologically inspired. So they are inspired from how the brain works. Neural networks, which is the foundation of deep learning, are general approximators. It means that they can learn any function, really any function. It's like a function is just mapping an input to an output. This is a function, exactly what you used to do in high school, what you call the function. And neural networks are general approximators. So you have some data set, and they can approximate how to transform that input to an output. And they can do that for any data set. Of course, there are problems that we are going to examine later, but they are like one of the rare models that are considered as general approximators. They can deal with different types of data depending on the model. They work surprisingly well. Even researchers are still like trying to understand why deep learning works so well. Still, there are papers coming like every here and then just to understand why this technology is working well. And they allow, this is a very strong concept that we are going to see in the next sessions, they allow for transfer learning in many cases. Transfer learning is when, for example, you train a model in a data set, and then you use that same model in a totally different data set. It's like you train a model, for example, you train a computer vision model that can recognize cats and dogs. You take that model and you use it for something completely different that can, for example, recognize lions and tigers. And it works surprisingly well. It allows for transfer learning. These are some aspects that we are going to see in the next sessions. So classes of problems that we can target with deep learning. So we have face recognition, how to recognize a person. We have object detection. Object detection is different than recognizing a person, because recognizing a face is to say that this person, like your mom or your dad, is in this picture. But object detection, you tell where it is. For example, you have multiple faces in a picture, and you can tell where is your dad, and you give like a bounding box, like a square in the picture, to say this is your dad, or this is what you're looking for. We have speech recognition. You say something and the model recognizes what you are saying, or even like recognizing the voice of a person speaking. Question answering, this is also a very powerful tool. It's like when you have some text or a book even, or books, and you ask a question and the model can go there and return the answers. It's quite a powerful concept. Text categorization, it's a very simple concept. You have a text and you say, the model can say what it is talking about, what topic we are talking about, like politics, economics, this kind of things. Video recognition, saying, what is this video about? What film? Maybe you can recognize what film it is. And some strong also cases like image generation. You generate a completely new images. Have you seen deep fakes? Have you seen like these deep fakes where you remove a face of a person from a picture and you replace it by someone else, and you can incriminate someone who is innocent? You have probably seen this kind of more of the images.
Yeah, there are even apps which are doing this.
Yeah. Are you using them?
Yeah, I've used last week. I've used one. It was funny. It's just it puts like different faces in clips, like for like singers, and it's just in a funny way that you use them.
not to incriminate anyone.
No. We're not there.
not yet.
No.
Okay. And
Sir, what about sorry? What about forecasting and time series classifications?
Yeah, that's a good question. It is possible to use RNNs for forecasting and time series, but we don't use them much there. Generally, in this class of problems, traditional methods seems to be still doing well, like ARIMA and the different traditional methods. So we are not using them a lot. There is still research ongoing on time series or deep learning applied to time series, but still it's not like as performant as we want it to be. Some companies like Google, they did a good job by using RNNs to predict electricity consumption, but it's like one of the few examples that worked better than traditional methods. Does it answer your question?
Thank you, sir.
Okay. So fraud detection, they are used mainly in banking. It's like when you have some text or some behavior in the system, and you can detect that this is odd or normal behavior. It's used a lot in banking, and there is a lot of like jobs going here as well, especially for banks. So now I like to start generally my deep learning courses. This is by a guy. This session for today is just a lightweight session. We are not going to go any deep in these models, just to see what we are going to explore in the upcoming sessions. So here I like to start my sessions with the images because they are very intuitive to understand. It's like humans are like very performant with images. So now let's see deep learning in vision, in computer vision. They are very powerful in automatic features engineering. I will explain what this is. Now, guys, how do you recognize a cat? How long does it take you to recognize a cat? Tell me, how long does it take you when you see a
Less
cat?
than a second. Less than a second is immediately.
Less than that.
Milliseconds.
Yeah, few
Immediately.
milliseconds. Yeah, you don't do. That doesn't take you any efforts. Like maybe reading a sentence is like more tiring than looking at the picture of a cat.
Yeah.
Why do you think you can? What is more complex? Like reading this strength is automatic in automatic feature engineering. It's probably it takes more energy to read it than to look at this picture. Yet the number of information in this picture is huge. It's not comparable to this sentence. Why do you think it's very easy for you to understand that this is a cat, and slightly more difficult to read 5 words? Why do you think this is the case? And it is very complex to understand that this is a cat. It's not. Tell me why this is a cat.
Because we know that since we were children, I mean,
But tell me, you are looking at it just logically, not just logically. Why this is what makes it a cat?
Eyes, shape,
Mustache.
features.
Yeah.
Yeah, all the features.
Yeah.
Small ears.
So yeah.
Fur.
Yeah, but
We have a knowledge base.
Yeah, a small fox can have this kind of ears.
Oh.
A mustache, even a human can have them. Or maybe they are slightly different. But
Not like this.
yeah. What?
Shape and
Sorry?
The size too.
shape.
Yeah.
The size,
Combination
yeah.
of-
Well, a fennec
combination of
fox
ears
can
and
have the same size. Well, it's like, and
Yeah,
well,
it's a mix of features.
it's a lot of features actually.
Yeah.
And you can't really. It's very hard to like assess them all of them, to put them in a list like this. I don't know how many features there are, but what is happening in our mind is billions of computations to recognize the cat. We take it for granted, but there are billions of computations happening in our mind. But these are happening outside of the realm of our consciousness. We are not conscious of them. There are neurons that are firing, billions that are firing to recognize this cat. Each pixel is connected to these neurons. And our consciousness is receiving the result directly, without a lot of efforts. And these neurons are computing all these features, are finding all these features. The shape of the ear, the shape of the eye, the nose, the mouth, the feet, etc., everything. They are assessing every single element of the cat. If, for example, we had a small part of the cat missing, you will know that there is something weird about it. Like it's just a small part here missing. You will recognize that it is a cat, but it shouldn't be like that. And you assessed it automatically without a lot of efforts. And these are like billions of computations happening in your mind without you realizing. And this is the inspiration for deep learning. Does it make sense for you guys?
Yeah.
Perfect. And in our mind, we have different neurons. And each neuron, we are going to see that each neuron is able to recognize a particular shape. It is trained to recognize a particular shape. And we have specialized neurons combined to recognize different things. So if we combine different shapes, small shapes like diagonals, verticals, horizontals, etc., circles, we combine a lot of them, we can end up with a cat or a dog or whatever, or a face. And this is what is happening in our mind. This is how it is happening. So this is an image. An image is just a group of pixels with different colors. What is happening in our mind, or even in deep learning, what we are doing, we are recognizing simple shapes like edges, diagonals, verticals, something empty, dark or white pixels, dark pixels. These are like eyes, very simple shapes. And then we combine these shapes because they are next to each other. They are combined to make even more complex shapes. For example, the eye is, say, like few diagonal lines and few horizontal lines. Like one vertical, for example, like here, to make that, I'm oversimplifying. Like, let's say this is an eye, the eye of a cat. So we have here one vertical line, few diagonal lines in this shape, and two horizontal lines. And if our neural network can recognize this, then this, and this. And if they are grouped in this particular order, there is another neurons that takes what we recognized, these simple shapes that we recognized, but translate them into more complex shapes, like here. Like a nose also is a combination of simple shapes, like this. And eye is as well a combination of simple shapes. So there are neurons that are specialized in simple shapes, and then neurons that are specialized in combining these simple shapes. And then other neurons that are also specialized in combining these other shapes. And we end up with what? A face. Like this face, or this face, or this face. It's like what is happening in our eyes is like stages of neurons. A neuron is just a function. We are going to see what it is. It's just a linear function, the simplest function you can imagine. And each one of them is specialized in something. And then we have another level of neurons that are specialized in something more complex, etc., until we reach something that is the most complex. Does it make sense for you guys? Do you have any question here?
It's very powerful algorithm. I don't know. It's like.
Of course, yes.
I guess this is CNN, no?
CNNs are used here. Used a lot here. It's the area of CNNs, convolutional neural networks. Yes. So, but the strength is even elsewhere. With traditional algorithms, we try to define these shapes. There are different ways, but we try to define them by hand. So we have a diagonal shape, a vertical one, etc. We define them. But with CNNs and deep learnings, they are recognized automatically. What micro shapes do we need to know? If we have an eye, do we need to recognize this kind of shape? So an eye, it's two. Let's draw it again. This is a very simple eye, the eye of a cat. So it needs to recognize this two types of shapes. So this one and this one are the same. This one and this one are the same. So we have how many here? 2, 4, 5, 6. 6 shapes. So if, for example, do we need to recognize a shape that is like, say, like this? Do we need it? Do we need this kind of shapes to recognize this eye? No, it doesn't exist here.
No.
It doesn't exist.
Yeah.
So we don't need to know how it looks like. So with deep learning, what happens, especially with CNN in this case, is that we lock in the shapes that are used in our case, and they are automatically detected. You are not going to do any efforts to know what micro shapes you need. Even in here, you don't need to specify it. The algorithm will detect them and will ignore anything that is not required. And this is called automatic features engineering. Sorry. This is a very strong aspect, automatic automatically doing the feature engineering. I will explain it more. So this is just, we are going to see this in the next sessions. This is just a feed-forward neural network, how neural network is. Here we have the inputs, and then we multiply them by some coefficients, some weights. We have another output. We multiply them by other weights, etc., and we end up with the output, the general output. But don't worry about this. We are going to see it in more depth in the following sessions. So, and just to also to draw some comparison with the human brain. There is a theory or a hypothesis saying most of human intelligence may be due to only one learning algorithm. It's like we have a zone here that is doing this learning. And it is one single algorithm that takes inputs. For example, it can even take auditory thing or visual thing to learn something auditory, and vice versa. It's like you can learn, like by hearing, you can picture a shape in your brain just by hearing. So there is like this kind of hypothesis saying most human intelligence comes from one single learning algorithm that is in the brain. And we are going to see these algorithms later, this class of algorithms that enable us to train a neural network. So this is a neuron of visual cortex. And this is another neuron for another visual cortex. It's what a neuron in the human brain is able to learn. So you can see that each neuron number one is recognizing what? What is this?
Vertical line.
Perfect. Yeah, it's a vertical line. So we have a neuron specialized in our mind, specialized in recognizing not one single neuron, probably a few of them, specialized in recognizing vertical lines. This one is specialized in recognizing diagonal lines.
Sorry, Rida, I'm lost. Why we need that? Like this one?
This one is just to compare.
You were talking about the human brain, and after you jump to this, sorry, I get lost.
This is also in the human brain. The human brain, we have neurons that are specialized in this kind of mini shapes, micro shapes.
I was thinking that algorithm or something like this. Okay.
Oh, it's very comparable. It's very comparable to what is happening in the brain.
Okay, got it.
So what we were looking at is something like that. So, and in our brain we have this kind of neurons, but what we are learning also when we are doing CNNs and deep learning, we are creating neurons, artificial neurons, of course, that are also specialized in this kind of shapes, simple shapes. And then we go on the top and we have like other neurons like here. So here we have neurons that, for example, this is just an example, that they are able to recognize simple things. And then we have here another neuron that is able to take the input from these neurons and will recognize more complex stuffs, like a nose or an eye here. And then we have others that will combine noses and eyes, etc., and create the face.
Okay, got it.
Okay.
Thank you.
No problem. So to build a neural network capable of such recognition, one needs a lot of computational power. Here, because in traditional algorithms, we need to specify, for example, for this image, for a face, we need to handcraft the features. We had to handcraft them to translate them, if you want, into if then else rules. If we have a diagonal line here, if we have, and this is clearly a lot of work. This is a huge amount of work to do everything by hand. Generally, we combine handcrafted rules with some traditional algorithms to get some results. But in here, in deep learning, you don't even need to handcraft this kind of rules. Where is a diagonal, a line? You can to tell it a line is 2 diagonal or 4 diagonal lines and 1 vertical line, 1 horizontal line. The algorithm will learn what it is by itself. This is the power. You just provide the data, and the algorithm will just go through it and understand what is an eye, what is a nose, only by itself. And this is really powerful. And it can end up with things that you never considered, like rules that are inside, that has been learned, but you have never considered. It's the same rules like when you see the picture of your father or anyone. These rules that are in your mind, they are intuitively learned. When I tell you this is a cat, there is a lot of intuition actually behind it. You cannot specify all the rules for this cat. Yes or no? It's very hard.
It's impossible.
Almost impossible. It's your instinct actually that is telling you that it is a cat.
Yeah.
It's your instinct. And this is, with deep learning, this is quite powerful. We are learning instinct. We are going as far as learning your instinct or any instinct of any person. And instinct is simply billions of computations that we can't explain by simple logic. If I can say so. Some people might disagree, but we can call that instinct is just billions of computations that we are unable to explain by simple words. And this is what deep learning is doing. It's learning instinct in a way that we can't describe. Are you happy with this explanation, guys?
Yes, sir. Yeah.
Yes.
That's why this is a very simple network. That's why we can end up with billions of parameters. Generally, a simple neural network that is capable of recognizing cats has like millions of parameters here. So, of course, we need to learn millions of parameters, and we use GPUs, graphical processing units, to train them. It's because of matrix. We do a lot of matrix multiplications with deep learning, and GPUs are very well optimized for matrix multiplications. Generally, GPUs got developed because of games. We didn't anticipate to use them for deep learning before. It's been like for a few decades that GPUs are being developed for games. And because of that, when deep learning came, we found that GPUs are almost ready for us to be used. Computational power. Sorry?
What about quantums? PC with quantum.
These are like another class of computation. You can use. I haven't documented myself a lot about it. It's like when you can flash through your data, all of your data at once, and you get you train all the data set at batches will be very large. But I don't have this a lot of knowledge about it yet. I need to document myself about this new technologies, and and not just GPUs are used. You can use other technologies like FPGAs that are like this kind of circuits of or ASICs, other circuits, but GPUs are used the most. And one of the problems with neural networks before, it was processing power. They needed a lot of processing power, and CPUs were never enough. GPUs were the solution because they were developed enough because of games. They were the solution to it, or I would say, if I could say, cost-effective solution. We can also we have talked about recognizing a face, a cat, or whatever. We can also have algorithms that can localize something, like driverless cars use this kind of technology. You have a scene, and you try to draw bounding boxes around objects and recognize them. For example, this is a person, this is traffic light, this is a car, a person here, and you can see we have a lot of bounding boxes. Like driverless cars, we need that. We need to recognize, localize what is what. Otherwise, they can't drive by themselves. So this technology is used extensively in driverless cars, this image localization. And so it's another class of CNNs that is used in here. Also in computer vision as well. Do you recognize these guys? Do you know them?
Fake faces. Okay. They are fake. Yeah? They are not true. They are fake.
They don't exist. Exactly.
Yes.
These guys don't exist in real life. They never existed in the entire history. Probably, I'm not sure, but probably they never existed, unless you have a proof against it.
Sir.
they look very realistic. What do you think, guys?
Yeah.
Yeah, it's like I was surprised.
They probably never existed in the entire history of humanity.
Oh wow, they look so real.
So real, amazingly real.
Yeah.
So convincing.
Sorry?
They are so convincing.
So convincing,
True.
yeah.
Yeah.
Yeah, amazingly convincing. And these are what we use with GANs, generated adversarial networks. They can generate data by learning from existing data. And they can generate things that never existed before.
Sir,
Yeah?
in the previous, would you go back to the previous slide?
This one?
Yeah. Is this a classification problem?
This is a localization problem. It's a little bit more than classification. So you need to recognize what this guy is, what this shape is, and draw the bounding boxes. It's harder than classification.
Okay. In classification problem, we got classes and labels.
Exactly.
Here, what we can get.
You classify the entire picture, but in localization, sorry.
Yeah. In this case, what do we have?
You have in the data set you will have the bounding box and what it is. So in your class you have the coordinates x1, y1, x2, y2, and the class as well. So you need to find the box and the class.
Okay, thank you.
So welcome. So this, guys, this is generated. This is one of the other level of deep learning. We can generate these faces and use them in something that is different. There are even like you can even in some models you can specify emotions, the emotion of the person, and you will generate a face like this with the required emotion.
Sad,
etc. This is quite powerful, guys. What do you think?
It's wonderful.
Yeah. Now let's have a look at NLP, natural language processing. We have seen examples for images. Let's see with NLP how to tell, for example, what is the topic of a text. So you have a text and you want to tell if it is about speaking about politics, about poetry, about history, this kind of things. This is a very simple classification problem for text. So generally, previous techniques or the old techniques, they work very well for classification in many cases. But for example, how do you differentiate between words that are written similarly but they mean different things? For example, brown color and brown name. Bean, what is the crop, and bean, the name.
Context,
orange as a fruit. Sorry? And orange, the fruit.
To the context, according to its context.
Of course, yeah, according to the context. Orange fruit and orange the color. So the word itself is not enough. We need the context, the word that are next to it.
So we go one by one.
Yeah, you look at them and you understand what orange means, this orange, well, what it is about.
It means one by one. It's like orange and after color, and we have to
see what is next to it to understand what it is about.
Okay. Okay.
I would like to also to mention the possibilities for NLP. We have text categorization, politics, etc., history, medicine, these kind of things. Question answering. Question answering is when you read few books, then you ask a question in plain language, you type your question, and you get the answer. And models are doing very well in this kind of class of problems. Sorry, did you say something?
A chatbot, like a chatbot.
For example, a chatbot, yeah. You read different piece of text, and the chatbot almost index everything. And when you ask that chatbot a question, it answers your question, and it can do a good job in many cases. We have document tagging. You can tell about everything that the document is speaking about, all the topics.
Summarization.
You can do some summarization. Is a bit harder, yeah, but you can still do summarization. named entity recognition, this is a simpler problem where you have different text, different word in text, and you can tell each word what it is. For example, where is the subject, where is the verb, where is this kind of things. Sorry?
Post tag.
Yeah, exactly. We can call it post tagging. Yeah, you tag the words by something. But you can even, for example, you can do it for this, or when you have they use this a lot for CVs. Where you have a CV, they parse it automatically, and they take the keywords of the technologies. And this named entity recognition can look at the keywords and see this is the name of technology. This is the name of the company where the guy worked for. This is a degree that he had. And it can recognize every word and what it represents and summarize the CV in something that is quickly to read by the reviewer. This is used a lot in CVs. And we have also the equivalent of the faces that you saw with text. We can also generate text from something, text generation. Models now, when we reach this chapter, this is the last chapter, we are going to see the traditional methods that are used for the NLP and also the new methods and the state of the art. Just to give something about them, some information about them, the old methods are what we call bag of words approaches. It's like we take the bag of words, each piece of text is a set of words, it's considered as a set of words. For example, a small stone fell on a big stone, and we convert it into something like that. We have two A's, one small, two stones, this one and this one. One fell, one on, and one big. So we convert this text into something like that. It's like a set. But you can see that we lose the ordering. When we do that, we are going to lose the order of the words. Do you agree with me?
Yeah.
Yeah.
Yes.
Do you agree with me? Yeah, we are losing the order. But it can still work well in certain cases. Even with just taking the words, what do we have in a document? For example, let's do an example. You are all guys familiar with a tabular data set like this. A simple tabular data set.
The CSV file.
Yeah, a CSV-like file. Yeah, exactly. You are all familiar with it.
Yes.
So here, for example, here we have, let's say a bank would like to give a loan to someone, and it has like some data set about which person was able to pay back and which person are not able. So we have here age, income, loan, country where the guy is living, and here we have payment. Exactly, we have payment. Did he pay or not? Yes, no, yes, no. This is a simple problem. Yes, no. So this is a simple data set. Do you understand what we are doing here? All of you?
Yes.
Please stop me if you don't. So we have different information. Sorry?
Go on.
Okay. So we have different information, and we want to create a model that will be able to predict if the guy is going to pay or not from this. But when we have text, we can't do that. Text is not organized.
Semi-structured.
It's not structured. It's unstructured. Semi-structured is when you have an HTML or something that has some form. But here it's totally unstructured text. So what we do, we convert it into something like that, and they become the features. So for example, we have a table here, and this will be A. This will be small. This will be stone. Sorry, my writing is awful here, but I don't have a choice.
You will have to write all.
Yeah, this will be fell. This will be on.
I guess you have to remove.
This is another thing. Yeah, exactly. It's removing empty words. Yeah, when we want to remove empty words. But this is another aspect. It's just to improve that generalization. So we can end up with this kind of matrix. With text, we do this. We are going to do examples in here, in this using this. So we transform text that was unstructured into something that is structured, and then we start building a model. That is how we do things in the traditional way. Do you agree, guys? Are you happy with this solution?
Yes.
So we are transforming something unstructured into something structured. So the features becomes the words that are appearing in my text, and the occurrence or a TF-IDF approach. There are different ways of in these values. And we put, for example, the occurrence. This is a simple way. The occurrence here we have 1, 2, 2, 2, 1. The next example will be different. And we create our model to, for example, recognize the topic, what it's talking about. But as I said, we are losing the order. We are just saying this text has 2 A's, 1 small, 2 stones, 1 fell, 1 on, 1 big. We don't have the order anymore. So there is something that is missed in this information. Deep learning traditional approaches, they do that. Deep learning approaches, they generally don't lose the order. They keep the order in the algorithm or in the data, and start to do something taking the order into account. One of the first methods, we call them RNNs, recurrent neural networks, such as the famous LSTM and GRU. For some time, these 2 methods were the state of the art. They produced the best results when it came to sequential data. Text is sequential data, like we have the order matters. And like images, in images, the spatial information matters, because a pixel that is in here alone doesn't mean a lot. 1 pixel black or white doesn't mean a lot. But the closest pixels to it can combine with it to make something meaningful. An eye, you don't need for the eye, guys. You don't. If you want to recognize an eye, you look at the pixels that are in the eye. You don't have to look at the pixels that are far apart, here or here. So the closeness in space matters between pixels. The closer they are, the higher chances we have that these pixels can combine to make something. Are you happy with this?
Yes.
All of you guys, are you happy?
Yeah.
Here, it's just 1 dimension. Text has 1 dimension, so the words are going to come 1 by 1. So what LSTMs and GRU do is to encode words 1 by 1. Take word and learn what you have, learn the model, take the next one, take the second, the third one. They take words 1 by 1. And this was the method of choice for some time. After it, we had models like that are based on the transformer, such as BERT and GPT. These are the state of art right now. Models that are based on the transformer. We have different models, but they are very close to these 2. And they don't rely in the same structure, like taking words 1 by 1. They take the text all together, and they produce what we need. And they are like they revolutionized the field of NLP. They also allows for transfer learning. RNNs they don't allow for good transfer learning. It was very hard to like train them on some recognizing some text and then take the model and use it in something else. But the transformers, they allowed that. We train a model into some data set, we take that model and we can use it in a different problem with some modifications, and they still work very well.
Transfer learning.
In transfer learning, yeah. Word embeddings as well. It's a very powerful technique that we are going to see later. What does word embeddings do? It takes words and transforms each word in the dictionary are transformed into vectors. So each word is not a sequence of characters, but it is a vector. But the magic behind it as you can see here, the magic behind it. When, for example, we have a vector of 2 dimensions. This is Apple, this is Microsoft, IBM, and Mango. When we train a model that transforms words into vectors, you can see that it puts Apple between Mango and Microsoft and IBM, because apples have double meanings. Apples have double meanings. And like Mango has 1 meaning, Microsoft and IBM have 1 meaning each, and Apple, because it has double meanings, it was put close to a fruit and close to a company. We can have here far apart something different, like words that don't share a lot with Apple, like steel or sea, this kind of word. They will be far apart. But the words that has something in common with Apple will be close to it, as you can see here. It's like words, or vectors representing words, will have meanings that are shared between closer vectors, closer words. In some embeddings, we can have even something like that. We take the vector for king and the vector for the word male. We did this operation king minus male, which are 2 vectors. We can do a minus operation between vectors, and we end up surprisingly with a vector for queen. For example, let's do an example here. Let's say we have a simple vector for king. King is represented by the values 2, 5, and the male is represented by, sorry, I can't remember, by 1, 0. Queen is represented, when we train the model, is represented by, for example, 1, 5. And these are things that we are, it's not us who are controlling these values. The deep learning model is learning them, is learning these representations. We are going to see how. The deep learning model is learning these representations, how to best encode king, how to transform it in the best way into a vector, how to transform male in its vector, how to transform queen on its vector. We are not intervening directly. We are just supplying the data set. And when we see how king is transformed into this 2, 5, male is transformed into 1, 0, we do a minus operation, and we end up with a vector for queen. And without any a modification from our side. We just have a data set that is, for example, Wikipedia or a lot of text, and we end up with this kind of encoding, which looks like magic, don't you think?
Yeah.
It looks like, and it's like happening by itself, deliberately. These are called word embeddings. There are multiple generations of word embeddings that we are going to see. There are contextualized word embeddings that are able to make a difference, that they will generate different embeddings if Apple is a company or if Apple is a fruit, depending on the context or what we call the surrounding words next to it.
Yeah, sorry. Mango here, it could be company as well. So it's clothing company.
Yeah, okay. Thank you for the precision.
Yeah, so you should have used another fruit.
Yeah, well, yeah. Let's assume it is not enough for our example, or we trained it for.
There's a brand as well. Yeah.
All the names are used.
Thank you for this. Yeah, well, anything can be used now as a name of a company. But this is just that's an example. But if it was not a company, and Apple is a famous company and a famous fruit, its embedding will be close to the fruits group. Here we will have a lot of fruits, and here we will have a lot of companies, and Apple will be in between. But the newest generation will be able to make this distinction. There will be an apple close here and another apple here, and the surrounding keywords will decide what it is, and we will have a different embedding. We are going to see that later. Here we are just looking at how to just an introduction to this. But you can see that, and generally these models are trained, for example, by using the whole Wikipedia. We take the whole Wikipedia and we start understanding the relationship between words. And by studying this, automatically, we are not doing anything as humans. We are not like, we are just launching the algorithm by itself to learn from the data. And it will end up with a representation like this, or even a more powerful one like this. This is a very powerful representation, where words have becomes like mathematical have mathematical meanings between them. Okay, guys. Now let's have a look at this kind of models. Can you read this text? You probably, maybe you have came across it. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. I don't know how to pronounce it. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. Well, this is clearly some imaginary work, sci-fi or sci-fi fiction. And then we continue. The scientists named the population after that distinctive horn of its unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, after almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. Dr. George Perez, an evolutionary biologist from the University of Laval, etc. Where do you think this text was taken from? When you read it like for the first time, like this, where do you think it was taken from?
The first paragraph it was from Kit's book.
For example, yeah, it could be from BD or something like that.
Yeah.
Yeah, some comics, this kind of things, like from books. Actually, this first paragraph was written by a human, and this was continued by an AI, GPT-2. What it did. This was from here. This part is a human text. It was fed into a model, and GPT-2 continued with this. What do you think with these 2 paragraphs, here and here? You can continue reading. While examining this bizarre creature, the scientists discovered that the creatures also spoke some fairly regular English. They started, we can see, for example, that they have a common language, something like a dialect or dialectic. Authors believe that the unicorns may have originated in Argentina, where the animals were believed to be descendants of a lost race of people who lived there before the arrival of Europe. It's impressive, don't you think?
Yeah, I think that this algorithm will surpass the human. Because they are doing everything.
It surpassed me in my writing abilities.
It's like writing. I'm talking about the writing, like writing skills.
It's doing better than me, actually. It's impressive, yeah, to see this kind of. It was generated by GPT-2 like a couple of years ago. This and GPT-3 was just released. It is a lot more powerful than this. And we are going, guys, to examine all of these models, from CNNs to GPT, BERT, and of course the foundations of neural networks, how they are trained, what is like the loss function, what is the loss function, what is the dropout, how to make a neural network converge, how to play with them. All of this, we are going to see it on the next sessions. Do you have any questions, guys? Here?
Using TensorFlow or PyTorch?
I think we are going to use TensorFlow. The difference between the two is not big. We are going to use TensorFlow and Keras.
Okay.
To do a lot of things. We are probably not going to use generative models. They take a lot of power. If you have a GPU, a strong GPU at your disposal, that would be awesome. Otherwise, we can try to use different free hardware. We can try.
Colab.
For example, yeah. For example, like Colab or other free stuffs. But if you have a GPU at your disposal, that would be awesome. If you can get one. Even something that is not super powerful, but something that will allow you to play with these models. Any question, guys? Are you at least a little bit fascinated?
Dr. Rida, can you hear me?
Yes.
All right. We've been taking the previous classes the months ago. Yes. Are these models dependent on the previous ones, or do we need to understand the first part to continue with this one, or just separate? They are separate.
Not necessarily. There is linear regression, for example, logistic regression are closely related to this, but you don't just need to understand what the others are doing. You don't really need to understand them deeply, but it's good to have an idea about them.
I mean, do you need to use them in a deep
No,
learning?
we are not going to use them. We are going to use some of them in the bag of wood approach, this one here, just to see to compare them with this. But you don't really need to be proficient at them, just the possibility to use them. That's all what you need.
Okay.
But that would be better if you can understand them well.
Yeah.
Any questions, guys?
We have two RNNs, recurrent neural network and residual. I don't know. What is the difference between them?
What did you say? Recurrent neural network and
residual. Residual. It's a word. Its abbreviation is RNN also.
So we have recurrent neural network and we have recursive neural network. Maybe that's what you mean. Residual. I don't know of a residual neural network. I know of the residual connections. And these are used mainly with different types of neural networks, the residual connections. And you will find them used a lot in CNNs, these residual connections. But is that what you mean?
Residual, like that. Voila. Residual.
You mean?
What is the difference with? According to ResNet.
So sorry, I don't understand what you mean by residual here. In what context?
What is the difference between ResNet?
ResNet. Okay, thank you. That's the residual connection. ResNet it's not a neural network. It's a form of connection that is used with certain types of neural networks. We are going to see that. Don't worry, we're going to see that in details. It's just a way to generalize better by feeding a layer of the neural network with a layer that is not directly connected to it, that came before in the past. And it works well for generalization and they allow very deep neural networks without losing a lot. The residual connection that they were introduced with the architecture ResNet. But RNNs are completely a different architecture. Residual connections are not an architecture in themselves. They are just a special type of connection inside the model, inside the architecture. But the RNNs are like an architecture on their own. We can use residual connections with inside of RNN when we have a feed-forward layer with it. But it doesn't happen a lot. We use them. Residual connections are used a lot in CNNs and also in the transformer. The transformer also takes advantage of the residual connection. Don't worry, we're going to examine this aspect deeply later.
Thank you, Rida, for the explanation. Just like I felt a bit lost. I don't know why. Perhaps I'm quite new to this subject. Yeah. So, yeah. Just quick question here for recurrent neural network, and is Is that like a method this or something else?
Well, it's fine. It's fine if you feel lost at this point, because what we are doing is just to draw a picture of what we are going to see. So a recurrent neural network is just, this is what we call a feed-forward neural network.
I have used this stuff in MATLAB, so I was doing some work.
This is a feed-forward. A recurrent is a different approach, where each input, when you feed an input here, you have an output, and this cell will get back the output as an input again.
Okay.
So when you feed the next input, you also feed the previous output. It's just a different approach. You take into consideration what happened in the past. Here we don't have the notion of past.
Right.
This is just one sample. Yeah.
Additional question here for the last training or the training that you did before. Is there any relation between them, this one and the other one?
There is some relation. Well, if you can master some aspect of the last training, that would be good. But you can go by just understanding what they are doing, what each model is doing. That would be sufficient.
Cool. Okay, thanks a lot.
Any other questions, guys? Are you motivated at least? Are you fascinated by this technology?
So much.
Yeah.
That's great.
The beginning sounds hard, but maybe if we go more deep, we're gonna get it.
Oh, it's just an overview. So it's normal that you haven't understood everything.
Yeah, sure.
Even I am confused. Don't worry.
I don't think so.
It's going to be fine. But what I wanted to just to see the capabilities. We are going to see everything in detail. Don't worry.
Yeah.
Just to see these capabilities of recognizing a cat, learning different aspects of an image, decomposing it, this kind of localization, generating. We are going to see how the architectures are, but we need a lot of processing power to this kind of models that can generate faces. But you can use the existing models for it.
No.
And then with text, we are not going to do generating text. It also require a lot of processing power. But we are going to see how we can train these models that are able to recognize text or to do question answering, etc. And the main thing is to understand their foundations and the intuition behind each model, what is deeply rooted into these models. This can work very, very well in interviews. In interviews, like they try to assess how deeply you understand these architectures and these models. And this is what you need to get. Okay, guys?
Yeah, it's all right.
Yes.
Yeah, like how can we train a model that takes without doing a lot of interference, and it can learn something like that. Relationship between words, when you look at Wikipedia, the relationship between words are kept in the mathematical production of the vectors. This is amazing if you can keep it.
Are we going to use Python for it?
Python, yeah. Python is the ideal language for these kind of things.
And then which software are we going to use with Python?
Probably TensorFlow and Keras. We are going to use that a lot. These are the libraries that we are going to use. But guys, the libraries and the programming language are not the most important aspect in here. Like programming language and libraries that we can have, Python is the top language for machine learning right now, but it can change in the future. We never know. Say for libraries, we have TensorFlow, PyTorch that are making a lot of noise this time, but it can change as well. Don't be tied to one single library or one single programming language. And what, you said something? Okay, guys. No other questions? You're happy with this? With what we are going to see?
We are scared.
Don't worry. Don't worry about this. You will be fine. You don't need to understand all of this in one go. We are going to, like, for each week, we are going to like zoom in a small aspect.
I know, it's like going. You asked if we are happy, so I told you I'm just scared.
But guys, when we are done, I'm fairly sure you will be able to get a job.
Inshallah, inshallah.
Believe me, I'm 100% sure that you are. If you understand this like at 60%, and you will be able to play with some source code and train in some models, I'm fairly sure you will be able to get a job in this discipline.
Good.
Inshallah.
Inshallah.
So no
sir,
questions, guys.
what about signal processing and time series? I want to learn more than on time series.
Well, it's not part of the syllabus here, as you saw, for time series.
Yes.
They are, if I can call it that way, maybe some guys who are working in economics will disagree with me and they will attack me. But generally, most models used for time series are rather simpler than this. So I would suggest that you look at the algorithms for time series like ARIMA, exponential smoothing, Hall filter, Prophet from Facebook.
They don't use deep learning.
No, they generally, we can use deep learning, like RNNs are used, but we rarely beat these traditional algorithms for them. So it's better if you use this kind of algorithms, ARIMA, Prophet, these kind of things, and they work fairly well.
If I can add something, Reda, if you can let me. I was involved to do some anomaly detection with some governmental services. And I tried a lot. I was stuck, in fact. Reda knows about it. I tried to apply autoencoder to do this analysis, to detect automatically the anomalies inside our system, etc. And I was not able to get any results. But after, when I start to use this algorithm, like this time series, they call it statistical learning. I start to use ARIMA, I start to use Prophet, etc. They work very, very good for me, and they got a very, very good result.
Fast, and they are very fast.
Yeah, and very fast, yes, and very fast. So that's why it's, if you want to do time series, I think the statistical learning is much better than this.
It's still, it's still better. We don't recommend, even when we talk to people, when they ask us, like different people around the world, they ask us if they can use deep learning for time series data, and we also tell them it's not really worth it at this point. We can't guarantee that you can improve your results, and you are going to use a lot of processing power to do that. So
problem, but
always like
my problem is that my test is time series classification using deep learning. I can't use
it's
ordinary.
a PhD thesis or what?
Yes, PhD.
Okay, well that's not fair to give that your supervisor gave you this.
Yes, I'm suffering.
Yeah,
I saw like there is a lot of companies, they provide this autoencoder, like to detect to look in fact to do like some forecasting. If you have like if you want to do like normal forecasting using the trend, etc., they use this autoencoder to simulate or to forecast the future. So you can look. There is good libraries. I can send you after some links. But I try it. I didn't get a good result like with ARIMA or Prophet.
It depends on his
I'm not working on forecasting. Sorry, I'm not working on forecasting problem. I'm working on classifications.
If you said classification, what do you mean? What do you mean by classification? Because it's time series. You know, if we say time series, we don't have classification. It's like time series with same data with some value.
We can still use classification for time series, yeah.
Yes, we have.
You can classify like the whole series.
EEG problem. EEG.
It's a brain signal.
Yeah, brain signal.
Brain signal. It's like you classify what it is. Like for example, you have values, and you say if this value is the brain is sick or the brain means something. This kind of thing. It's like you don't forecast the next value. You classify this, how the series is. What this means.
The heartbeat, for example.
Okay, yeah, it's another scope. It's not like my case. Yes.
Yeah, it can be similar. Are you like required to produce a new algorithm or just to do a study?
I don't know. Actually, now I'm working on I might use transfer learning, but I'm afraid that I won't have very good results like such ARIMA.
We can talk about it later, because I think it will take a lot of time to speak about this topic right now. But I will be happy, like, to talk about it. I'm sure Farouk will be happy as well.
Of course.
Okay.
So, guys, any other questions? And I really want you just to be motivated, because this technology requires a lot of energy and a lot of motivation. But once you get it, it's really, really worth it. So I really the main aspect of this session, of the first session, is to get your motivation to its highest level. That's what I am expecting from it.
Is it the only thing that we need? Motivation.
Right now, right now I want your
come on, guys.
Nice point.
So far we have it.
So that's perfect. That's what I want from this session. Don't worry about the mass, what we have seen, etc. To understand everything. That's totally normal that you will not get everything in the first session. But your motivation is what I want to be high. You can see that this technology is like almost magic. It has like, it can generate text, it can generate faces. From unsupervised text to Wikipedia text, you can have something that is ordered, like king minus male equal queen. So this kind of representation, without the intervention of humans. Just from the data, you can get this kind of rules. It's really, really like a super powerful technology. So if you are super motivated, that is the main goal of this session. Next time, we are going to zoom in each aspect of this technology, and we are going to understand it better. You want to say something, anyone?
Thanks a lot. I have a quick question, Reda, please. What do you think is a good idea to compare my results using another machine learning algorithm with deep learning? I see that deep learning is giving great results, so I don't know if it is a good idea to like validate my results with comparing with deep learning.
Oh, yeah, of course. Yeah, it's very good to compare your results with deep learning. If I remember your thesis, you are doing some form. You are creating rules that can help with classifying what is what, and deep learning can also be used for localization.
Yeah, so, but my results will like seem less good than deep learning.
Depending on the data set. Let's talk about it also separately, because it's a huge topic as well. Your thesis is quite good and quite big. Let's put a meeting, and I'm happy to talk about it and go through it. Because
thank you, and thank you very much for the presentation.
No problem, guys. So thank you guys for your attendance. Today it's a smaller session than what you have later. And see you next week.
Thanks, Reda. Thank you.
Thank you.
Yeah. Thank you, Reda. Thank you.
Please, Reda, don't forget to send me the link of linear regression as I asked.
It's in my mind. Don't worry.
Okay, thank you so much. Thank you.
Okay. Thank you, guys.
Can you also share the slides with us, please?
Yeah, sure. Yeah.
Okay, great.
Thank you. Bye.
Thanks, Reda. Thank you.
Thank you. Goodbye.